Okay, so welcome everyone. So my topic is about machine learning, machine translation actually. This will be today the primary topic, and I will focus on the TectoMT machine translation system, tree-to-tree transfer on a deep syntactic layer, tectogrammatical, which we developed here for several years. But some parts, actually all of it, will be somehow connected also to machine learning, especially discriminative models. So first, I will just in the introduction show you or remind you how TectoMT system works, and what do I mean when I say isomorphic transfer. This will be a key, one of the key topics of this talk, whether we should, what's the isomorphic or non-isomorphic transfer. I will shortly also describe Moses, a phrase-based system, and the differences between Moses and TectoMT. There will be a short quiz for you, so let's do it some interactive. And then I will describe how to cast the task of machine translation as node labeling, so to apply some techniques well known. And actually, probably the largest part of the talk will somehow go through the history of this institute, well, only since 2008, and the various ideas how to improve transfer phase of the TectoMT system. So, this is the schema of TectoMT, and it's the classical analysis, transfer, and synthesis schema. And we analyze the source sentence up to tectogrammatical layer or something which is similar to the tectogrammatical layer, but it's modified for our purposes of machine translation. And this source language structure is transferred to the target language, abstract representation. In this talk, I will focus mostly or only on the transfer part, unlike in other my talks. So it's actually not so important how the representation looks like, whether what phenomena, coreference, or whatever is handled there. I'm interested in the general algorithm how to convert tree structure representation of a sentence from one language to another. So here is the, let's say, the tectogrammatical tree, T-tree, and in this case we are translating from Czech, a sentence strojový překlad by měl být snadný, to English. Machine translation should be easy. That's the correct translation. And what I want to illustrate with this picture now is only the fact that in this case, the sentence can be translated isomorphically, which means that it's one-to-one node. So beat is translated as one word, either to be or to have, and we need just to select the best lemma or word, which is the label in this case. So, strictly speaking, isomorphic is from the graph theory defined, and it's not only one-to-one, but also that the structure of the tree remains the same. So the shape of the tree is the same. Yes?
I see like 6 words in the Czech sentence and 5 words in the English one.
Yes, good point. So, the sentence was analyzed up to the tectogrammatically, which is an abstract representation, which means that, for example, all functional words are not represented as nodes. They are somehow encoded into attributes of these tectogrammatical nodes, and those attributes are not shown on this picture. So it's a very good point, because if you are going to apply if you hear about tree-to-tree translation somewhere, usually it's just surface syntactic tree, where each node corresponds to one token, surface token. And in this case, you can guess that it's only very rarely possible to translate one word to one word from one language to another. Even in related languages, there are cases where it's not one-to-one. But most of those cases are caused by the functional words or some other phenomena which somehow disappears or is abstracted on the tectogrammatical layer. So this is the primary motivation for the tectogrammatical layer. For the transfer on this layer, some 6-7 years ago, I did an analysis of errors done by TectoMT system, and only 8% of the errors were caused by the assumption of isomorphism. So by that time, and actually it's still true, we basically, we expect that the transfer is isomorphic, that it's one-to-one. So we are not able to translate some sentences correctly. I don't know, typewriter should be psací stroj. And these are two tectogrammatical nodes, psací and stroj, and only one in the English. So we will translate it not correctly, but we have some ways how to handle it. I have a slide about this. And this is one node, and there are just two labels how it can be translated. So yes, please interrupt me anytime, just raise your hand or immediately ask. So the isomorphic otherwise is clear. It also means that I cannot, for example, switch or the direction of a dependency edge. This would, I could still have like 5 words to 5 words, but if the dependency structure changes, then it's not isomorphic. Okay. So now step aside, look on the state-of-the-art phrase-based statistical machine translation, where probably the most popular toolkit is called Moses, or open source toolkit. And what are the differences? So in the basic approach with Moses, there is no linguistic analysis needed. You just need to somehow tokenize it into words, and the rest is pure statistic. And so, as you have seen in TectoMT, we need tagger, parser, lemmatizer, coreferencer solver, and so on. In Moses, the source sentence is segmented into phrases, which can be 1 word, 2 words, but subsequent, so it's a linear structure. And each phrase is translated independently. There is a model which says actually the translation probability. There are about 5 kinds of probabilities or scores. But what I wanted to point out here is that those probabilities or those scores are not influenced by the surrounding of the phrase. So the phrase is translated independently on the sentence in which it appears. There is one exception in the end or during the decoding. There is a language model which somehow binds those phrases together or says the probability of the whole sentence. But except for this, each phrase is translated independently, but you have many ways how you can segment the source sentence into phrases in phrase-based SMT. And actually, virtually all those possible segmentations are considered, or it's a search task, so the phrases can be overlapping. But in the end, only one segmentation of non-overlapping phrases is selected for the source sentence, and these phrases are translated. So the final score or probability of the translation is based only on the one segmentation in Moses. Any questions? Okay, so now comes the quiz, the interactive part. For those of you who can speak English and Czech, could you guess, is it possible to translate English word prime as vláda? And actually the question is, in which context? Some of you know this is my favorite example, but anyway, say if you know.
Prime Minister?
Yes, Prime Minister. Prime Minister can be translated into Czech as předseda vlády. Another translation could be premiér, but let's have this. And as you can see, the adjective, it's translated as a noun. So you may say it's not a translation. Vlády is not a translation of word prime. Well, you may say it, but in TectoMT, this can be done. TectoMT can do this, even in the isomorphic setting. This is the point of this slide. So it seems like strange translation, but it's still possible in the isomorphic setting. So even you would say that this is a phrase which cannot be translated independently, but still it's isomorphic. So how to formalize such a translation rule? When I say rule, I don't mean that automatically that it must be manually written. It can be automatically learned rule with probabilities and so on. So probably here is the word lemma we are translating, and on the tectogrammatical layer we have something called formeme, which says that this word is actually adjective in attributive position. And we also need a context. So we need to know that the dependency parent or head, governing node, its lemma is minister. So only in this context, prime can be translated as vláda, otherwise not. And probably we will also need to say how to translate that in Czech, this for me means it's a noun in genitive case, and that the parent is lemma is předseda. You can see this is somehow not original tectogrammatical attribute. It's the surface case, but it's for practical reason we use it. Yes?
Yeah, no, it's just when looking at these examples, for me at least, prime would be something which may correspond to předseda, and vlády, which would correspond to minister, because if you have ministers in plural, you would probably like to, in some context, to translate it as vláda. So why have you chosen?
Yes, the reason is that the dependency structure, that actually the red node depends on the black node in both languages. So in this case, it is isomorphic. If you somehow would like to translate it, as you said, the other way around, it would not be isomorphic. Although still it would be one-to-one node, but you would need to switch the direction of the edge. So, okay, so let's have. Yes, here I say that when I want to translate prime minister as premier, then this is not isomorphic. Let's have another quiz question. Is it possible to translate find as přijít, and which context? So, yes, I have found it easy. Přišlo mi to snadné. Any other example? Find a solution, přijít na řešení. Okay. The find out, I expected this answer. Actually, not me, but my wife told me. And on tectogrammatical layer, we have find out as a lemma. The phrasal verb, the phrasal particle is concatenated. So this actually would not be represented as lemma find. So it's not this case. And you said find a solution. So this is also not the case, but it could be. So my example I had in mind is Agatha found that book interesting. And the translation, Agatě přišla ta kniha zajímavá. So this is somehow more difficult what the correspondence is. So how to formalize this translation rule if we want our system to be able to translate this in this way? Of course, you know there are other possible translations, but what would we need to say when you remember here these two boxes? So what should be there now? So you think that the interesting should be translated as přišla?
No, if you have children or
Yes.
child, find.
So this is the verb find, and its dependency child is interesting, and it's some adjective. We call it complement. In English would be probably called predicative, I think. That only in that context, yes. So, sorry. It's a question. If we want just to translate find as přijít, probably only the complement child is okay. We actually don't need to know the lemma, interesting. It could be find it green or whatever. But so only the formeme is important here. But probably we would also like to translate, actually you can notice that Agata is a subject here, but in Czech the subject is the book and Agata is in dative case. So we need also do some changes elsewhere. So this is a motivating example for so-called tree-let transfer, where I don't want to translate one tectogrammatical node or even just the lemma independently, but I want to select a bigger part of the tree, not the whole tree, but some part which is connected with dependency edges, and say this must be translated at once. So tree-let is defined as a subgraph, connected subgraph of the tree. It doesn't need to go up to the leaf, it can be any part. And we translate one tree-let to another tree-let, so this I call it tree-let pair or translation rule. Okay, and also the example here is that, as I said, I need to know only the formeme. I don't need to know what are the lemmas of those green words. So this somehow motivated the idea how to represent the tectogrammatical layer in such a way that there is just one label for node, which will be on further slides. But let's now look how it is now. When I simplify it, probably oversimplify, so then the tectogrammatical tree for machine translation, the two most important attributes is the lemma and formeme. And there are a set of so-called grammatemes where the grammatical categories, tense, number, and so on are saved. But those usually are translated, that the singular is translated as singular and so on. So I'm mostly interested in lemmas and formemes. And the current solution in the best performing TectoMT is that these are just two attributes of the node, of each node. I can imagine it also as I can concatenate it. So if I have an algorithm that can translate labeled tree from one language to another, but the algorithm supports only one label per node, one attribute, then I can say, okay, there is a one label which has find and verb in finite verb, and it's just concatenated as one label. And another way how to do this is to actually split each node into two nodes such that the formeme is the upper. That's important. So also you can imagine it that if you have words, let's say find and book, then the formeme is on the edge. It's somehow label of the edge, which is, I think, even from the linguistic point of view, okay, that actually the subject is a label of the relation between find and Agata. And also, it's so not only from linguistic point of view, but also from the statistical modeling point of view, where now I can take only this tree-let, so find, and these three green children. So this is a tree-let of this I call it interleaved tree with, and when I want to distinguish it, I call this subnode, converted from the original node. So it makes sense that still it will be just a treelet, and I can take only connected subgraph of this, the treelets. So this means that I say that I cannot take a rule which says find and book as a child translate as something, but I don't care about the phoneme here. And I think this is not a big disadvantage. I think you almost always need to know the phoneme, or sometimes you don't need to know it. It's somehow, when I say find and child interesting, you somehow know that the only possible phoneme is this complement or predicative. Okay, any questions about this? Yes?
Yeah, I just don't see how this is so important relative. So maybe because, I don't know, what the teachers look at things in the tree context and the source.
As you have seen, it's equivalent to the previous. I've just mechanically converted it, so it has the same properties, but I think it's a good abstraction when you think about the transfer or the linguistic or statistical properties to imagine this tree. And as I said, sometimes when I was inventing some new algorithms, it was easier for me to just abstract from the linguistic and say just, okay, let's come up with an algorithm which translates labeled tree to a labeled tree, and just one label per node. And I know that this representation is somehow well suited for this.
I could imagine this works well for grammar, but I could imagine it hurts the lexical aspect of the translation at the same time. For example, you might say that if you talk about, I don't know, writing a book, so it does not matter so much whether the book is the object or whether it's some kind of other adverbial modifier somewhere.
For example?
Writing text for a book, something like that. It's still the same context. The book is in the context, but it is different.
Yes.
I don't think it's so much for the
Yes, we can discuss it later. If you can come up with some examples, I could imagine maybe like I go to Prague or from Prague, where this is the preposition is encoded in the phoneme, and somehow probably the go can be translated in different ways, in different languages, but when I know it's Prague under as a child, probably some translations are more probable than other, but it's not so important whether it's from or to Prague. But even in this case, these are just two prepositions, so the data sparsity just half, or twice, but it's not a big problem in this case. So I still think this is a helpful abstraction. So what about the grammatemes? The current approach is that grammatemes are translated in post-processing. These are rule-based blocks, which somehow I know that staff should be translated as zaměstnanec, but actually it's singular in English and plural in Czech, and so on. So there is a list of exceptions, but we've always wanted to have it somehow automatically learned, so we can enhance this representation with where each grammateme will be a child of the lemma, and it will be the leaf, no other children will be on this, and it could still work. Here I am not so sure if like sometimes maybe there is some dependency from the statistical point of view between the phoneme and the grammateme, or between a child and the grammateme, so there maybe you will need to have features which are created by treelets with gaps. But I don't want to talk about this much. I have not tried this approach yet, but
I mean that the features on the target side might be important for generating query runs, or when it's on the source side, then you can add anything you like.
I meant on the source side. Yes, I can add such features. Yes.
I think on the source side you're not limited by anything, because the source
Yes. That's a good point, actually, whether it's discriminative or generative. And in some approaches, these are based just that I take a three-let and completely translate it. And I cannot really say, I won't translate this part. There will be a gap which will be translated later on. In some approaches, this is not possible. In some approaches, it is possible. So, yes. Yet another interesting option, which I want to try as soon as possible, is to encode the grammar themes concatenated with the lemma, but only if the grammar theme is changed in some unpredictable, in the exception way. So when I have staff and zaměstnanec, it always will be, or I think it will be single to plural, so it must be encoded jointly with the label. But if it's singular to singular, then that's the default option, and it don't need to be there. Of course, in Czech, on the tectogrammatic, we somehow have the gender, which is not in English, except for personal pronouns. This should be handled in other means, because there we can have a lexicon of Czech nouns, which says which gender is.
For example, police is plural.
Yes, that's also a good example, the other way around, from plural to singular.
You have the same one, so it won't be one capture, but I don't understand. Because you are saying that encoded with the lemma, but only if the lemma changed.
Only if the phoneme is changed. Thanks for clarification. Only if the phoneme is changing from singular to plural or past tense to present tense, then I will encode it with the lemma, no matter whether the lemma is the same in the second language or not. Okay. So let's now focus on ways how to handle the non-isomorphic transfer. The current approach is that we have some blocks within the transfer phase, but which are not part of the main algorithm, but are applied either before as pre-processing or afterwards. These are sometimes rule-based blocks, or can be also automatically learned, which basically say, okay, when I'm in 1994, in Czech I need to have in year 1994, so there is a rule which adds the word year, rok, in Czech. There are some algorithms I will present which can natively handle the non-isomorphism, which can learn how to translate, as I said, a tree-let to tree-let, but a tree-let will have different number of nodes or the topology. So there are some algorithms which handle this natively. And also a nice trick I would like to try as soon as possible is to convert the training data into isomorphic case, into isomorphic trees. I don't want to go into details, it's not implemented yet, but the basic idea is that I will have a special label, for example, for the lemma, delete this node. So when I have more nodes to one, from 2 nodes to one of the nodes will say delete me. So formally it will be isomorphic, but there will be simple post-processing block where if label delete me was selected as the best, then this node will be deleted. And somehow similar for the other way, where actually if all options say this one node should be translated as 2 nodes, then it's okay. I will translate it as 2 nodes. But if there are competing options, one says translate it as 2 nodes, and another says translate it as 1 node, I need somehow to select. So there are some problems, but actually I can change the 1-to-1 rule, so it's formally 1 to 2, but the second node on the target side says delete me. So somehow the non-isomorphism will be local only within small tree-lets, so from the big picture will be still isomorphic. So I think this is also a good idea, because this allows me to use some algorithms which are only for the isomorphic transfer, and I want to try this. Yes.
I'm not very familiar with this, but post-processing, the pre-processing, or the conversion as you now described, you have to decide basically just on the source side, right? Because otherwise during decoding, what would you do?
Yes, so in the pre-processing, post-processing, these are currently rule-based block or sometimes even hacks, like just quick fixes, and these are done on the target side. Or basically, I know what was the source side, but it's done during the transfer. This is more principled approach, and actually, this N-to-1 is done during the training, and it adds this label to the target side. This 1 to N actually needs to be done during the decoding. And I said I don't want to go into the details. You need also sometimes to encode the change of the topology. If the new node is added as a child or as a sibling or as a parent, there may be other cases, but I want to do some statistic. I think those 3 cases will cover 90% of the non-isomorphism, so it will be enough like this. Even in the isomorphic case, or even in 1-to-1 or 2 nodes to 2 nodes, you can have you change the topology, so this can be used also for other kinds of non-isomorphism. So now I'm switching to the last part of the presentation. The history of TectoMT, the framework was created by Zdeněk Žabokrcký in 2005, I think, like that year. But the first system was 2007, I'm not sure, and the results I found, all those were for 2008. And here I'm focusing only on the transfer part. So here was some initial implementation I will describe soon. And these are blue score differences. So the green are the improvements on the same test set. Actually, meanwhile, the system was improved also in other ways, but these are always like just by adding this HMTM idea, we get 1.5 points blue improvement. And so this was joint work, and this was joint work with Aleš Tamchina. These are only mine ideas. And as you can see, they did not work. When I tried them originally, actually I wanted somehow to substitute this last working idea, HMTM plus Maxent, with something new, with some better transfer. And when I started, it was about 10 points worse or 5 points worse. And I tried, and in the end, it was only 3 points worse or only 2 points worse. But still, I was not satisfied with this, so these are not published. And just last year, I was able to somehow substitute the transfer with something new, and I get a small improvement, but I was quite happy with this. But since then, I had not time to continue with this because, yes, sorry?
Can you briefly describe what's the initial
Yes,
baseline?
I will describe it. There are slides. I just here wanted to show the blue scores on one slide. There were also other improvements during those years, almost 1 point blue. Yes? These are additive. So actually, the Maxent added 0.8 on top of this. Actually, once we had the HMTM, this became the baseline. And so this is -2 minus this last baseline. And yes, the TectoMoses didn't work, so I just throw it off. So this is -3 relative to this. Yes, yes. Yes, yes. These are somehow orthogonal. These are improvements in parsing and rule-based blocks wherever. So basically, when I add this, all scores here go up 1 point. So why have I not done anything since the last year? There is a EU project Qt Leap for machine translation. Incidentally, so I thought, oh, it's good, I can work on my PhD thesis, but somehow we had to build the system for 7 languages, so 14 language pairs, always to English and from English. And so I think it's quite successful, at least relative to our expectation. We have now working system for Portuguese, which is better than the Moses. And for English to Czech, which is the language direction which is most developed in TectoMT, we were able to get almost 9 blue points improvement in just 2 months, basically, this year. So it's a joint work with those 3 guys there. And you may wonder, so now it's easy and before you were just lazy or whatever. There is small but important difference. This is another domain. It's translation of IT domain text with text about computers or question and answers. And actually, most of those 8 points came just, this is translation. The scenario is that there is someone you ask in your language and someone answers you, but the answer in English, and this is translated to Czech, and actually the answers mostly contained imperatives. Click on this window and do this. Imperatives were not handled by our TectoMT system correctly enough, so we just improve handling of imperatives and get 8 points blue. So you cannot trust the blue scores, but still, I think these scores are somehow comparable. This one is not, but still. Okay. So now you ask, how does the baseline look like? The baseline was really naive. We have a translation model, both one for lemmas and one for phonemes. The principle is the same, and it's just a relative frequency probabilistic model. And we call this static somehow because it's not dependent on the, this is just the source lemma. So probability of the target lemma given the source lemma, independent of the rest of the sentence. So it's not context sensitive. Therefore, we call it static. It gives always the same translation distribution. Moreover, in this naive baseline, only the topmost translation was used, the one with the highest probability. All other were just disregarded. And the translation of lemmas and phonemes was almost independent. So I think first, phonemes when translated, then lemmas. There were some small rule-based blocks, I think, which somehow said, okay, this lemma doesn't go with this phoneme, but basically it was this simple. And it was in 2008, but the evaluation in WMT shared task was in 2009, early in that year, and TectoMT was the war system, both according to the automatic blue scores and according to the manual human ranking. Otherwise, the blue scores did not agree with the human ranking. The best system according to blue score was Moses by Ondřej Bojar, but according to human scores, the 2 best winners were the commercial systems, Eurotran and PC Translator. If you are wondering how it looks today, or I think even 2 years ago, these 2 systems are the worst. And now even TectoMT outperforms there according both to blue score and human ranking. I'm not sure, maybe we don't have the newest version, but and of course Google and Moses quality went up with bigger data and new algorithms, but this is just a view to the history. Okay, sorry. Yes. I think the single biggest improvement was in 2009 we applied with Zdeněk Žabokrecký hidden Markov tree models, which is tree equivalent of the hidden Markov models you are probably familiar with. And the advantage is that we could exploit target language tree model, which models the probability of a node given its parent. So probability of lemma and formeme given the parent lemma. Actually, we disregard the parent formeme, but it could be there. So what it does, I call it tree language model, although it's not Ngram language model. So it doesn't predict the probability of a sentence. It predicts only these probabilities in the tree. And it first checks that the lemma and formeme are compatible. That the formeme can say noun in genitive case, but the lemma cannot be adjective for this, this basic compatibility. And also, or more importantly, the compatibility of parent and child in the dependency tree. So it selects the globally optimal labeling of the tree. Viterbi algorithm is used for this. So actually, if you are familiar with the Viterbi or HMM, so the red edges are the translation probabilities corresponding to emission probabilities in HMM, and the green is the tree language model corresponding to transition probabilities in HMM. Okay, in 2010, we still were using the HMTM and the tree language model, but we switched from the static translation model. Here is for lemmas, but for formemes it's the same. And we have not switched completely, but we had added a new model and interpolated those two. And the new model is context sensitive, or in other words, a discriminative model which does not predict the joint probability of source and target, but actually we only care about the probability of the target word given any features from the source tree. So again, the most useful feature is the source lemma, but there are also many other features, and you can see those are the blue here. So we care about the lemma of the parent, lemma of the child, formeme of the parent, lemma of the previous node in the surface word order, following word in the surface word order, and so on. So here the sentence says, he agreed with the unions to cut all overtime. And the question is how to translate word cut. And actually, in this case, the Czech equivalence of cut could be translated as chop, saw, trim, shorten, lower, and so on. And in this case, I think it's either the cancel or abolish or zrušit. Dohodl se s odbory na zrušení všech předčasů. So it's not the most common translation of word cut, probably, but in this context, when the thing you are cutting is overtime, you need to use, probably the lemma of child will be the important feature for this model. So any questions about this? Okay. So now the unsuccessful experiments of mine. So in 2012, I said, Moses is still much better than TectoMT. Let's steal the good ideas from Moses and import them into TectoMT. So let's use the analysis and synthesis from TectoMT, but substitute the transfer with Moses. So instead of HMTM and the Maxent, let's use the phrase-based decoding. But we have trees on the input and we want to have trees on the output. So how can we use the phrase-based decoding? And the idea was simply linearize the tectogrammatical tree, so the lemmas and phonemes only. And Moses supports factored translation, where you can usually, it's used for word forms and part of speech text. But I have used this for lemmas and phonemes. And so I trained this with Moses, and then in the decoding translated. So I had a linearized target language sequence of lemmas and phonemes. And then I projected the dependencies from the source tree to the target tree. And after some debugging and so on, it somehow worked. We improved a lot, but still, as you could see, it's worse than the original TectoMT. If you are interested in the details, I think this still could be tried, but we would need to improve the implementation of factored translation in Moses to allow so-called asynchronous phrases. The basic idea in Moses is that it segments the sentence into phrases, and if there are two factors, then they are segmented synchronously. So the same length of the phrase is used for both lemmas and phonemes. This is not optimal for our purpose. Unlike the part of speech text and word forms, where actually the part of speech text is some fine, coarse-grained representation of the lemmas, but in our case, phonemes and lemmas are something different. Okay. So another unsuccessful approach was motivated by the Bayesian statistic, and I also don't want to talk about this too much because it was so unsuccessful that I had not implemented it. Maybe it could work somehow, but I somehow gave up this. But the idea was to use so-called Chinese restaurant process on parallel tree bank and learn optimal segmentation to the treelets, or actually treelets pair. So which treelet in the English corresponds to which treelet in Czech. And I hope that this could somehow discover the phrases which are reused often, so which are good to translate in one treelet. And so if you are interested, I can tell you details later on. There were some problems, some were rather technical, some were more theoretical, that instead of the Chinese restaurant, which is quite easy to implement, I had to use pit manure process, which is somehow more difficult. The Gibbs sampling suffered from local maxima, so I tried to use slice sampling, or maybe anything would be better. But probably the biggest problem was this, that when we want to translate cut grass or cut taxes, each time the cut should be translated with different Czech verb, and it depends on the object, whether it's grass or taxes. So I would like to have this as a treelet pair, cut grass and sekat trávu. But basically, the Chinese restaurant process or the pit manure doesn't know anything about the translation, or what is our objective measure, the blue score or accuracy. It cares more about the reusable segments. And actually grass as trava, it's quite reusable. It's always seen in the data. So so similarly taxes translating as daně, it's also a good treelet pair. And cut as sekat somehow also works. So it was splitted, and I didn't see any way how to force it to have this in one segment or treelet. There is a newer work where actually the author, Dan Gildea, confirmed those 2 points. I'm correct, they also had to use this, and they used it for something slightly different, and it worked, so still, you may try it. So another approach which was also not so successful, and I presented this, you can remember, 2 years ago. So you may remember these pictures. So I also just will briefly say what is what about. Easy first treelet based transfer. Again, the idea was to preserve, to have the trilets translated at once. So I can somehow, similar as phrases are preserved in Moses, I want to preserve the trilets. And the trilets may be overlapping. So how to select which to translate? And there is a nice idea of guided learning, which was applied to tagging and to parsing. And I wanted to, or I applied it to machine translation. So the idea of guided learning is that it jointly learns two tasks or two aspects of the task. First, how to translate which trilet, in which context, and there are some features, and in which order I should translate it. So the idea is to start with the easiest part of the sentence and translate this. And then when there is a difficult word, probably the found is the difficult word here, I will have the rest of the sentence already translated, so there are many more features I can use for the decision. So the difficult decisions are left to the later stages, and it automatically learns what are the easy decisions and what are the difficult decisions. So this was the advantage, and I still like this idea. Another advantage is that it handles natively the non-isomorphism in the transfer. Although I have not tried this, I still used only isomorphic rows, but it could be used with non-isomorphic. The problem was I would like to have some features looking on the language model or the tree-language model. But if there is only partial translation, I was not sure how to apply it when part of the sentence is missing. So should it be that it's completely wrong or some neutral score? Or, yes, it could be probably somehow worked out, but I was not sure. And as you could have seen in the table, there is a similar algorithm as EasyFord, which I called Interpol, and it was 1 point blue better. So this was another reason why I switched to the Interpol. And yes.
Sorry,
Yes.
I'm not sure what you mean by the problem with three-legged people. So if you are choosing how to translate into the word, so because you will have a partial translation, so you can look at all the features, not only on the words that are already translated. But that's true for all the competing translations for the position, so it will be a problem. Like if you don't know the following word, so all its features will be 0, but for all the alternatives that you are considering, so it doesn't make a big difference.
I'm not sure if I'm able to describe it now. One problem is that I took a logarithm of the probability, which is very negative number. So if you take, the feature is not there, so it's 0. Yes, it's discriminative, but the language model is a feature, which I call a summary feature, and its value is estimated using relative frequencies as a probability, or it can be smoothed as done in language modeling. You know, when you are translating left to right, you always have the left context. But here I could use the language model both on left context and right context. Actually, it's in 3, so upper context and several lower contexts. And if some of them are missing, I was not sure. I had to use some number, otherwise it would not be. Yes, it was in one model, but I was not sure what should be the value of the language model feature. And it's, maybe we can discuss it later. There were also other problems with the implementation. Actually, some of those problems are also common to the interpolation of trilets that I had to implement the machine learning algorithm, some perceptron-like, again from scratch, and then I found, oh, here is the Wallpaper Wabbit tool, and this was how it goes after this slide. But now I will describe the interpolation. So it's similar to EasyFirst in the aspect that there is one feature or actually this feature has one weight in the model which counts the number of nodes or subnodes in the treelet, so the size of the treelet. And I somehow wanted to model that whether I should first translate the big treelets or the small treelets, or I think this could be a useful feature. And many other features are possible. I can have lexicalized feature, I can look on the part of speech text and so on. I can do combinations or quadratic features, the interactions. I can quantize the language model score can be bucketed into several binary features and so on. So now what's the difference between the easy first and interpolation? In interpolation, all matching rules, treelet pairs, are applied at once or in parallel, and their scores are summed up or interpolated. So each rule has some weights. It says, okay, there will be such a probability, and then the probabilities or scores are interpolated. So I need to know which node corresponds to which target node, or which target node coming from different treelets actually corresponds to one node, and if they say the same translation, this translation should be boosted. So unlike, if you remember one of the first slides, I said in Moses, many segmentations are considered, but only one is used for the final probability. Here I want to use actually all segmentations for computing the probability of the translation and the modeling. And it's also, there are some related papers in phrase-based SMT that this should be the theoretically correct approach, but there are some technical problems with this, which some of them I don't face in the tree, but okay. So the problem is this does not handle the isomorphism. If I want to know which target node corresponds to which one, I basically need to have just one-to-one correspondence there. But as I said before, there are other ways how to handle the non-isomorphism, and no guided learning is applicable here. An example, in the sentence, Agatha found this book interesting. The score of when I'm translating the word interesting and want to know what's the score of translation zajímavá, I don't care about lemmas and WordCamps for word forms for simplicity here. So first I can use the maximum entropy model, all the features and their weights multiplied in addition to what is new here. And here is one model which says only the, when I'm translating just the lemma. So interesting to, to zajímavá. This model translates a treelet pair consisting of two subnodes, lemma, which I am translating now, and a for meme which stands only for the context. So interesting and complement translate as zajímavá and adjective in a nominative. So this is the one which was finally chosen translation, but I can interpolate it, or I will interpolate it also with this rule, where the for meme is translated using some other for meme, but now I am considering only this lemma. So all the treelets where interesting is translated as zajímavá, their probabilities are summed up, or actually these are the weights, so they are interpolated. And similarly for these two models consider 3 subnodes, and this one considers 4 subnodes. So, any questions about this? So still the idea is I want to translate treelet at once, but now I said, oh, it's even better than in the easy first approach because I can translate all the treelet at once and somehow find a globally optimum probability or model. So I said, like, the easy first is better than, from my point of view, than the maxent, and this Interpol is better than the easy first approach. And now comes the tricky question. How is this Interpol actually different from the Maxent approach from 2010, which was on the previous slide? So it's a question I know you had not enough time to fully understand this, so I will show you the answer. It's basically the same. What I did was something like this. I said, oh, I'm going better, and now I'm actually using formally very same model as in the Maxent. Logit stands for logistic regression, or multinomial logit is the synonym for Maxent. So the Interpol model approach can be trained using maximum entropy classifier or some other multi-class classifier, it doesn't matter. Still, I can use the tree language model and the HMTM. This is the same for Maxent and for Interpol. And actually, the Interpol is equivalent, just there are additional features. But as you know, if you have here something about machine learning, the features are what usually matters, not the decoding algorithm and so on. So here the features I call summary features, where the value of the feature is pre-computed on some big training data or whole training data. So in my case, this is the value of the feature, this score. And this can be actually a relative frequency. So similarly as in Moses, in the phrase table, the probability that this phrase or treelet will be translated as this phrase or treelet. Yes?
So the weights were trained using the Maxent? Like the interpolation?
Yes. Actually, I had my own perceptron-like algorithm, but it could be trained with Maxent, I realized. And therefore actually used Vowpal Wabbit, which doesn't use actually maximum entropy, but reduction to binary classification, but it's not so important difference.
So what you are saying is that you use the same approach, but added some features and because
Yes, I had not done many experiments with the Interpol. I found that I have some technical problems with my implementation of the perceptron, and that I would like to use the Vowpal Wabbit. So actually, the Vowpal Wabbit, the score which was plus 0.1 score, is improvement of this Interpol actually. But now I don't look at it as I'm translating whole treelet at once. I'm still translating one word at once, but the features consider source side treelet. So it is in the Maxent, the difference is that in the Maxent, I looked at the lemma of parent and lemma of child, but never at both. There were no feature which would consider the quadratic or of those, or lemma of this node and formeme and lemma of the parent, or those trippers which correspond to the treelets in the subtree representation. So what I actually did, I added those lexicalized higher order cubic or quadratic features into the Maxent, or actually not into the Maxent, but into the Vowpal Wabbit, and it worked quite good. And then I said, and on top of this, I can add those summarized features which actually have the relative frequency. And this is still work in progress. What I did, I really used the relative frequency, so without this, and it didn't work. Actually, it worked somehow, and then by accident, in the decoding, I forgot to put there those features, and it worked even better. So I said, oh, here is something wrong with those features. And the problem, at least I think, I'm convinced, is that I trained it on the training data, or estimated these probabilities, these relative frequencies, and then the Vowpal Wabbit went through the same training data. So once it saw the example on which this was trained, and consider some very rare translation, which was seen just once in the data and only in this way, this translation. So, and it's maybe a very long treelet. And this actually says, oh, this treelet is very helpful. I see it now again that it worked, but it's the same example based on which I have estimated this. So I think this results in that the bigger treelets are considered more helpful than they actually are. So I want to do experiment with this -1. Yes, kind of. Internally, I call it -1 smoothing, but it's not probabilistic. It could be done as well, yes. And just, I call it summary feature, which is a new name, but it's actually used in Moses. Actually, Moses doesn't do, usual Moses doesn't use any lexicalized feature. There are about the 10 or 12 scores or models which are actually those summary features. Then another feature is the word count, which is not summary, but yes. So now the last year I am using Vowpal Wabbit, which has this nice logo, and it's really, really fast. Like what I was before training several days on 100 computers on our cluster, on the whole chain. Now the training is completed in 1 hour on one computer, 2 cores. And actually, so it takes much, much longer to extract the features, the training data from the TreeX files than the machine learning itself. Vowpal Wabbit is well known for parallelization. It can run on 1,000 machines. I don't use it because I don't need it, actually. The chunk is small data from Vowpal Wabbit point of view. And it's well optimized. It's stochastic gradient descent, but there are some optimizations on top of it, like Adagrat, if you know about this. And it can handle a combination of dense and sparse features, which is not true for the original stochastic gradient descent. So here I said the summary features are dense, which means that for each example, for each, let's say, word I'm translating, I see this feature with some value. Or maybe I have bucketed it into according to the size of the treelet, so there are 10 features, but each time I see one of those 10 features, no matter what word it is. But the lexicalized feature, when it says dog translates as pes, if the parent is bark, it's quite rare, sparse. So it's sometimes a problem for machine learning to train both sparse features and dense features, but Vowpal Wabbit can handle this, and I use something which is called cost-sensitive one-against-all reduction to binary classification, so it's not really Maxent, but it's another way how to do multiclass classification. And I use logistic laws because I want to have probabilistic interpretation. I don't really care whether it's a probability or not. I normalize it that it sums up to 1, but I still want to use the HMTM. So far, I have not integrated the language model, the 3 language model scores into the Vowpal Wabbit. I plan to do it sometimes, but so far, I still want to be able to re-rank the suggestions done by the translation model, to re-rank them with the HMTM and with the 3 language model. So I want them to somehow correspond to probabilities at least roughly. Yes. So I think I have talked too long, and still you may have some questions.
Yeah, thank you very much. So we have space for some questions. So before you think about
Given up on the non-isomorphic transfer when you're using the Vowpal Wabbit?
So far, yes. or actually I'm using only the post-processing blocks which are already in the TectoMT transfer, so it's comparable to the previous approach. This was also one twist in my mind. Originally I said I need 3 LEDs because I need a non-isomorphic transfer. But then I looked on some errors in the translation and I said, well, but there are many errors even in the isomorphic cases. What I need is to have a better source context. I needed 3 LEDs on the source as features, but not really for the non-isomorphism. Of course, there are cases where the non-isomorphism is needed, and I plan to do it, but I think it's not the top problem of current TectoMT.
Thanks.
Can you go back to the Interpol?
Yes.
Slide? Yeah, I'm wondering, the list of various scores that enter into the calculation look an awful lot like marginalization.
These scores.
Is there? Yeah.
Yes.
But
these are,
the
as I said,
question
relative frequencies, and even better with the -1 smoothing.
Is there really some marginalization going on, or can it be described in terms like these?
I'm not sure if I understand the question, but I will try somehow to answer it. There are 2 ways how what features I can use in the Interpol model. One is to use only these summary features. So I will have only, let's say, those 1, 2, 3, 4 kind models. I had a model which had actually just 10 features, and it performed quite good compared to the TectoMT. The trick was that each value of that feature was computed from the dictionary, or let's call it phrase table. It's on trees, but the idea is the same. So this was one. So no this Maxent score, only those scores, those summary features. It worked quite well. Then what I tried, and what is actually the plus 0.1 score, the best so far, in that case I don't use these features, and I use only the discriminative lexicalized sparse features, but unlike in the original Maxent, I have there features which look on the source side on this concatenation or combination. So I look on the cubic, quadratic, and like 4 times features. So there are many more features than originally, but Vowpal Wabbit can handle a big number of features. So probably this was not about the marginalization, but
no, but it thanks. It answers
okay.
what I meant.
I have a related clarification question to that. So you are training the weights, giving the lexicalized like assumption, like you are training it using the context separately, or like the weights WL, WLF.
As I said before, sorry, I can train only these 10 features, or I can train only those 1 million features, or what I would like to do, train on 1 million plus 10 features to combine both. And I think if I estimate this score correctly with the -1, I hope it will help, but I had not time to try it yet. And the question?
Okay.
It's answer, okay.
institute, I mean the former forms of this institute, date back to times when, I don't know, only 2 of you have been born, or maybe none of you have been born. And the name, I mean, you may have heard, is Zdeněk Kirchner, who was the author of our first system of machine translation from English to Czech. And when he was very angry, well, it was those times when statistical machine translation was supposed to be science fiction or something like that, if mentioned yet at that time. And so it was a rule-based system, of course, a small one, restricted one, but it gave some results. But very often the results were not very good. And the author was once extremely angry with the system and with the machine because he got these incorrect results. So he gave as an input the English sentence, "This machine is not very intelligent." And you may wonder what he got out in Czech. Tento stroj je velmi inteligentní. So the machine was that intelligent that it did not accept any negative appraisal of its function. And Zdeněk had some, well, it was not just by chance. I mean, he had some explanation for the fact why negation was translated into positive. I don't remember exactly what, but that was it. So I hope your system will not do that, or maybe is more intelligent to translate negation as negation.
It still happens with Moses system, as Rudolf can say that negation is a common error. I hope it's not so common in TectoMT. It should not be, but...
Okay, it was just to conclude. I would like to invite you for the next week talk on Monday, where we have a guest in the Fred Jelinek series, Professor Nicholas Escher, a specialist in semantics, logic, conversation, discourse. And he will present a talk, a rather general talk on discourse. So I hope that you will enjoy his talk. So thank both to Martin and to you that you have come, and see you next week. Thank you.